ID, the Future, a podcast about evolution and intelligent design.
What does it take for life to exist? To hear some tell the story, once a place in the universe has the right conditions, the right physics and chemistry, life can readily arise, and those same favorable conditions of physics and chemistry will then more or less inevitably lead to a great diversity and variety of living organisms. Indeed, in our earthly environment, life is so ubiquitous we can easily take it for granted, and we might even be tempted to think it's easy to generate and maintain life. But what's really required for life to exist beyond the physics and the chemistry? Hello, I'm Eric Anderson, and joining us on the show today is Dr. Howard Glicksman to discuss what's actually required for life and some of the remarkable engineering challenges that have to be solved in order to maintain a living organism such as ourselves. Dr. Glicksman practices palliative medicine and has been a longtime contributor to the debate over evolution and intelligent design. He's also co-author of the wonderful recent book, Your Designed Body. In addition to being just an all-around great guy, I should add. So welcome, Howard.
Thanks, Eric. It's great to be here with you today.
So, Howard, we often talk about the fine-tuning of the cosmos to enable life as evidence for design. We talk about the fine-tuning of our local environment, having a habitable planet in the habitable zone, and the myriad other conditions required to have a life-permitting environment. And so some people, even design proponents, might be tempted to think that once you've got all these carefully coordinated conditions in place, then the hard part's done, that life can inevitably move forward based on this favorable mix of physics and chemistry. But as I understand you, you're saying not so fast. And I'm glad you were able to participate in our recent conference on engineering and living systems, which we held in Denton, Texas. And in your presentation, Howard, at the conference, you mentioned that even these highly favorable conditions of the cosmos and of physics, even if they're designed, aren't going to naturally lead toward life. In fact, just the opposite. What do you mean by that?
Well, yeah, Eric, my thesis basically was that, when bottom line of Darwinism, and even I think theistic evolution people with the front end loading of the physics and chemistry, is that they think that the laws of nature, when left to their own devices, can cause life, but in reality, they actually cause death. Mm-hmm. Unless life comes up with some innovations to combat or leverage them. In other words, life has to solve the hard engineering problems that the laws of nature throw at it. And so that was what my talk was about. I'll just give three quick examples so that people can sort of understand where I'm coming from. One example would be the laws of nature. So you're talking about motion. We all know you need energy to move something against its inertia and friction. So, for example, you have blood in your body and it has oxygen and all the nutrients you need for your cells. However, it also has mass. So it needs something to move it. And, of course, the innovation is your heart. Okay, the heart, using energy, the heart pumps the blood throughout your body. So that's an innovation. Just the heart, where does the heart come from? A second example would be, let's talk about gravity. Obviously, gravity makes everything fall to the ground. So when your heart pumps, not only to move the blood down to your feet and linearly, it also has to be strong enough to move up to your brain when you're standing up. So when you bend over and let's say you're working in the yard and you stand up and you feel a little dizzy, and that's a sign that basically the gravity is getting in the way of blood going to your brain. And you'll notice that within a second or two, that usually goes away. And what's going on there is that your nervous system is detecting the blood pressure, that the blood pressure is reduced, and it sends out, through the sympathetic nervous system, it sends out norepinephrine, neurohormones, to make the heart pump harder, and for the downstream arterioles to tighten up to elevate the blood pressure so that dizziness goes away. So there's another innovation. Mm-hmm. A third one would be heat transfer. Probably a lot of people don't know that cellular respiration is only about 25 or 30% efficient. So most of the cellular respiration that's going on in your cells is releasing 70% of that energy is released as heat, and obviously becomes worse when you're exercising. So because of heat transfer, your core temperature is going to go up when you're active, and the problem that you got is that the enzyme systems, metabolic processes in your cells and the cell membrane work best in a temperature range between 97 and 99 degrees Fahrenheit. And if you start getting too high or too low, it doesn't work right. You get up about 106, 107 degrees Fahrenheit, and your cells are going to disintegrate, basically. So luckily, we have a thermoregulation system in our body that not only can we sweat, but also blood vessels and the superficial blood vessels in the skin can dilate and allow the body to give off heat through radiation and conduction. So there's 3 examples of innovations in the human body that have to be there to work against the laws or the forces of nature.
Yeah.
And I would go ahead.
Yeah, I was just going to say, so let's talk about this first one for a minute, because I just want to see if we can help our listeners get a grasp of this a little bit. So you mentioned friction. So let's talk about a car, because you've got energy and you've got friction, and you're talking about overcoming the friction. So the way that physics works is that we've got some friction between the car tires and the road. And that's what allows us to move forward. That's what allows us to turn when we need to turn. And yet we have to push against that friction. We have to battle that both on the road and with respect to the air resistance in order to move forward and accomplish what we're trying to accomplish with moving the car down from point A to point B. So there's this push and pull, if you will. Yes, the physics exists. They are what they are. The friction happens. The friction coefficient happens to be what it is. But we have to have a mechanism that's designed and built to handle that, and in some ways to counteract that and both utilize it. I think both things happen at the same time in order to make this work the way that we want to do it. If we just say, well, wouldn't it be great if we had no friction in the universe? Well, yeah, you might be able to go somewhere with little energy, but you wouldn't be able to turn. You wouldn't be able to stay on the road, do those kinds of things that you need to do in order to get from point A to point B. So both of those have to be there, and the friction isn't allowing us to drive. It's simply a factor that exists that we have to handle and we have to overcome and we have to deal with as we're trying to build something like a car. Does that kind of example help at all in terms of understanding what you're talking about in terms of friction with the blood and the heart pump?
Yeah, I think it does. But on top of that, then you've got another problem where friction can become a problem with all the moving parts in the car.
Right.
So
true.
on top of that, you need to have oil, you need to have lubrication.
Yes.
Because so there's several. So that's the whole point. There's several ways that the laws of nature, forces of nature, like friction, are good. Where, like you said, you have this innovation where we're able to we're able to leverage friction by making the car with wheels, etc. But also we have to combat the friction by using energy, through the energy of the combustion, for using fuel in the combustion engine, and also oil to lubricate the moving parts. So those are examples, and they don't just come all on their own, basically.
Yeah, I like the way you described that, because this really points out the fact that something that exists like friction with physics doesn't in and of itself either lead to a car or not. It's just a factor that has to be overcome if we're trying to build a system that's going to operate in this environment. And yes, we can leverage it for the driving, but we also have to counteract it in terms of the engine and the pistons moving and lots of other moving parts that need to be lubricated, as you mentioned. So it's something that the engineer has to take into account in terms of building the system, but the physics itself doesn't give you the car.
Yeah, and what I would say is that what's always I found frustrating, which made me start writing about this, and also I think culminated in the book with Steve, because getting the engineering perspective, is that if you look at the explanation from evolution, the Darwinian perspective, it's very simplistic and unidimensional. It just talks about the parts and they're existing. So you got a gene or gene regulatory network, but it doesn't really get into how everything works, not only at the cellular level, but the total body level, which is, we deal with very quickly in our book, within the chapter of the cell. We do talk about that energy, ATP, et cetera, and the kinesin, moving proteins or moving things within the cell. But then we get into the body. And that's sort of that was the basis of that talk that I gave. And I would just add, basically, from my perspective, the bottom line to Dr. Jim Tour's perspective, he's basically saying the same thing. The laws of nature, when left to their own devices, cause death. They do not cause life. And what he's basically saying, he's the expert on origin of life. He's basically saying, from my takeaway message is, look, I'm an organic chemist. I'm a specialist that I know what happens with chemical reactions when you leave them on your own. You don't have any intelligence doing something, changing things like the Miller experiment, et cetera. And basically he's saying you can't even make carbohydrates, fats, proteins, or nucleic acids, never mind a cell, with the cell membrane, et cetera. And so what I talked about at Cells was I said, okay, we're going to let you, it's a thought experiment. We're going to let you have the cell. We're going to move on to the next step, which is basically about water and its solutes. Because, we hear when someone finds a drop of water anywhere in the universe, they say, well, or in the solar system, well, you could have life there. And that's true. I mean, you do need water, but we do know that any doctor will tell you that water can be good, but if you don't have enough of it or you have too much of it, you can die.
Right.
We know that we need water. You get dehydrated, but also you can drown in water. So water by itself, it has to be in the right places, and same with the chemicals that are within it. So that's sort of what I talked about at Cells.
Right. Well, let's dive into that a little bit. So, yeah, there's the big push by NASA, of course, search for the water, which makes sense if you're going to try to search for organic life. But, yeah, I think you're right that there's sometimes a little bit of a simplistic view, at least popularly, that, hey, if there's water, then inevitably we're going to have life arise as a result of this. And Jim Tour's work, as you showed in terms of the original origin of life, is that chemicals on their own, as he says, don't have any desire or a tendency to turn into a living organism. It's just not true. In fact, they tend to degrade, they tend to break down, they tend to go back to their basic constituents. And so let's go ahead and grant that we have a cell, somehow on the earth. I think most of your work deals with multicellular organisms. So tell us a little bit about some of this work with respect to a multicellular organism like you and me. What's required for, say, cellular respiration? What kind of energy? Those kinds of things. Talk to us a little bit about that.
Well, actually, for what we're going to do today, I think that sort of goes off on another tangent, really. But certainly, your cell needs to have cellular respiration for energy, and the cell needs energy to do various things. But I want to deal with let's say you've got a cell with a cell membrane and DNA and everything that's in there, and there's a whole question: can that happen on its own? But this is the very first thing that you have to have, or the cell won't function. And so, what I want to comment about is water and its solutes. So water, sodium, potassium, and protein. So basically, 60% of your body consists of water, okay? And 2/3 of that is in your cells, your 30 plus trillion cells. And 1/3 of that water is outside your cells. It's called the inside the cell is called the intracellular fluid. Mm-hmm. The water outside your cells is called the extracellular fluid. And of that fluid that's outside your cells, 80% of that is actually surrounding your cells. It's called the interstitial fluid, fancy word for saying the water between the cells. But 20% of that water is in your intravascular volume, or in your blood system, okay, arteries, veins, etc. And so that part is the part that is important for multicellular organisms, because you've got to be able to pump blood everywhere, and you have to have enough water in the intravascular system. But what we wanted to talk about first today is about what's going on. I'm going to look at this at the cellular level. And
sure. So just so everybody catches this again. Yeah. So inside the cells is about 2/3 of your water.
Right.
Outside of your cells is the other third. And of that other third, you're saying 20% of that's in your bloodstream, essentially. We can think of it that way.
Right.
And the other 80% is surrounding the cells, what's called the interstitial fluid, you're calling it?
Right, interstitial fluid. Right. So it's, although it's not germane and maybe to what we're going to talk about today, it's important to understand that the interstitial fluid acts as a bridge between the intracellular fluid, and the intravascular fluid. So basically, if you're breathing, the oxygen goes, the oxygen jumps onto hemoglobin, the hemoglobin goes out into your capillaries, and it releases the oxygen, and then the oxygen goes by diffusion. It goes through the capillary into the interstitial fluid, and then from there into the cell, right? Okay. And likewise, your cells are using up oxygen, making carbon dioxide. So the carbon dioxide goes out of the cell, can pass through the cell membrane. It goes through the interstitial fluid, and then from there into the capillary, into your blood. So just to get a concept of where water is in your body and how this all works is, once again, that the interstitial fluid, the fluid surrounding all your cells, acts as a bridge between the cell and the intravascular fluid.
So we've got cells that have a lot of water in them. We've got cells that are surrounded with water. How does the cell maintain its volume and its chemical content to survive?
So this is the key thing. So the first thing before we get into, just to mention that, is that the key thing that people need to understand is that the cell, in order for it to survive, like you said, needs to maintain its volume, but it also needs to maintain its chemical content. Here's the key thing. The chemical content inside your cell is the exact opposite of what it is in the fluid outside the cell. So inside your cell, intercellular fluid has a high amount of potassium and a high amount of protein, but a very low amount of sodium. The fluid outside your cell has a high amount of sodium, low protein, and a low potassium, okay? So in order for your cells to survive and work properly, especially nerve and muscle cells, is because they're excitable and they have what's called a resting membrane potential, where the inside of the cell is negatively charged, and inside the cell membrane is negatively charged, the outside is positively charged. And part of keeping that all working properly is making sure that they have the right amount of chemicals inside the cell. So,
okay. All right. So the protein's easy to understand. We got proteins in the cell, right? Tons of proteins in the cell.
Exactly. Right.
So the sodium and the potassium. Let's mention that one more time, because this is going to be critical as we go forward the rest of our discussion. So
sure.
where is the potassium high? Where is it low? Where's the sodium high? Where's it low?
Okay, so for a normal cell, your cells are high in potassium and low in sodium. Okay. If I was to give you the units, it's called milliequivalents, but basically the number for the potassium is 150, and for sodium it's only 10. Okay. But for the fluid outside your cells, the number for sodium is 140, and for potassium it's only 5. So you see the extreme difference. Mm-hmm. There's an extreme difference. It's not like it's like 80, 70, 90, 50, whatever. No.
Right.
High amount of potassium inside your cell and an extremely low amount of potassium outside your cell, and very low amount of sodium inside your cell and very high amount of sodium outside your cell. So once you understand that, now we want to talk about the laws of nature, because we're saying that the cell has to maintain its volume and chemical content. Okay. And there's two laws of nature that affect basically what you have here is two systems next to each other, two compartments of fluid. They're interfaced with each other by the cell membrane. Mm-hmm. All right. So we know, and so there's two laws of nature, forces of nature that are going to be at working here. One is called diffusion, and the other one is called osmosis. So let's talk about diffusion. Diffusion basically is when you put two containers of fluid next to each other, and they're separated by what's called a permeable membrane, which means that the solution, let's say it's a salt solution, 1% compared to 2%. You got two solutions, different concentrations. So we're trying to mimic what's going on in the cell, in the body. And it's a permeable membrane, which means that the water can pass through and also the salt can pass through, right? So diffusion says basically that when you put these solutions, separate them by a permeable membrane, because of Brownian movement, the high concentration, the salt is going to naturally move from high concentration to low concentration to make it equal. Over time, what will happen is, and if you do experiments, most people have done this when they're in medical school or they've done physiology class. So you see this happen. So the diffusion thing is natural so what's going to end up is if one side's 1% and one side's 2%, after everything equilibrates, both sides are going to be 1.5% in between. And here's the key thing. The volume will not change because the solute can go through. So let's look at that with respect at the cell. This is where life can leverage the laws of nature. We just discussed that about oxygen and carbon dioxide. Oxygen and carbon dioxide can cross the cell membrane very easily. Okay. Now, the oxygen level outside your cell is always going to be higher than it is inside the cell, because the cells are always using up oxygen. So once we said the oxygen comes from you go through the lungs, it comes through your capillary into your interstitial fluid. Interstitial fluid oxygen level will always be higher than inside the cell, because as soon as it goes in there, you're doing cell respiration, you're using that, right? So you have this, what's called a concentration gradient. You have a situation where oxygen's high outside the cell, lower inside the cell. So by diffusion, it just naturally goes through, right? Mm-hmm. Don't have to have anything special. Great. The laws of nature work great in this case, right? And then you have the opposite for carbon dioxide. The carbon dioxide level in the cell is always going to be higher than in the interstitial fluid, and particularly in your blood, because your cells are making carbon dioxide. And so by diffusion, it's a concentration gradient. It's higher in the cell, lower in the interstitial fluid and inside the intravascular fluid. So carbon dioxide goes straight out. So that's a good thing. Okay. Now we're going to look about diffusion and sodium potassium. Remember, we said that in order for the cell to live properly, it has to maintain its volume and also chemical content. We just talked about the sodium potassium. In the cell membrane, the sodium and potassium can cross through as well. So the natural thing that diffusion is going to make happen is that the sodium is going to have a tendency to go into the cell because it's high on the outside, low on the inside, and it's going to make potassium from the inside of the cell go outside the cell. And that's sort of not a good thing, because ultimately over time, if left to its own devices, you're going to have the same amount on both sides. And we've just said, without getting into all the details, but the resting membrane potential, we just know physiology, everyone knows that the cell has to maintain its chemical content to live, and so does the fluid outside.
Okay. Yeah. So, and we can talk about why that is in a minute, but just to sort of put a simple statement on that last part, if you ended up in a situation where everything on the inside and the outside of the cell membrane were the same, so that all the chemicals have diffused back and forth, you end up with essentially a situation where you've got a homogeneous mixture. You have no life. Okay. And one of the things that people think about, particularly in Origin of Life, and they think about is how do we get and maintain this distance from equilibrium? Life has to maintain itself outside of equilibrium, but in its own state, homeostasis, of course. But how do we get out of that equilibrium and maintain it in a way that we have the things that we need inside the cell, the things that we need outside the cell, outside of the cell? So, yeah, so diffusion left to its own devices, I guess you're saying, Howard, would kill us, would kill the cell.
Right. And now we've also said, like, when your body's in equilibrium with the environment, you're dead.
Yeah.
But here's an example when the cell and the fluid inside the cell and the fluid outside the cell are in equilibrium, your cell's dead and you're dead as well. So but you're right. I mean, that's exactly your point is very well taken. Homeostasis. This is an example of trying to keep, and we're only talking at the cell level. We're not even talking at the body level. We're just talking at the cell.
Yeah. So again, just one more thing here before you move on to osmosis. So it sounds like what you're saying is that diffusion works for oxygen and carbon dioxide because they're moving in the direction that we want them to move for our system to function. Okay, like back to my car example. If you're pumping out the exhaust,
exactly,
and it naturally leaves the vehicle, great, that's where we want it to go. But then you're saying potassium and sodium need to have different concentrations on either side of the membrane, and they're not naturally going to move where we want them to go. Is that right?
Exactly. You got it perfectly. And I love the way you put it, because the thing is that it just so now here's an example where someone could say, well, the laws of nature cause life because, oxygen can diffuse and carbon dioxide diffuse. So life in this situation is sort of realize, hey, I don't need any special thing to make this happen. This is exactly what I want to do. I liken this to, if you think about with respect to this diffusion, or it's like when you look at the weather and they always say, they can tell in a high pressure area to a low pressure area, that's where the winds are going to go, or water coming down, gravity going down from high to low. It's the same mechanism going on. So this all works out great for life. Life is smart and says, hey, okay, for carbon dioxide and oxygen is great, but what do we do about sodium and potassium? That's not we got a problem there, potential problem.
Okay, we'll get to that in a second, but tell us about osmosis first.
Okay, so now osmosis is another way that, and this gets a little more complicated, but let's go back to that solution we just talked about where you have two solutions separated by a membrane. One is 1% salt and the other one's 2% salt. But in this case, it's called a semi-permeable membrane. What that means is the water can pass through, but the salt can't. All right? So remember, in diffusion, it was permeable, which meant the water and the salt can go through. So you ended up with 1.5% and the volume didn't change. But in this situation, it's a situation where the salt can't pass through. So in this situation, once again, the solutions still have to equilibrate to 1.5% somehow, right? And the way that's done is because the salt can't pass through, the water moves from an area of low concentration to high concentration. So as the water moves out from the 1%, that's going to make it start moving up to 1.5%. And as that water moves over to the side that's concentrated with 2%, it's going to dilute it. So it'll keep going over there until both sides are 1.5%. And that's great. But the difference here, though, is that the volumes have changed. So so you've got two solutions now. They both have 1.5%, but the water has moved from one side to the other. And now the volume on the side that was higher concentration has more water than the one with lower concentration.
Okay, so hang on. Let me picture this. So I've got my bucket here. It's got a membrane down the middle, a semi-permeable membrane. I've got the same amount of water on both sides, but I've got a different amount of solute
on
the two sides. Okay, so what you're saying is going to happen, Howard, is that if our membrane won't allow the solutes to cross, which is what we talked about earlier, when the volume stays the same, the solutes just cross the membrane and we end up with the same concentration. What you're saying in this case is that the semi-permeability will prevent the solutes from crossing from one side to the other, but that will actually draw water over to the side with higher solute, correct? So that we end up with, my two levels, one of them is going to go down a little bit and one's going to go up a little bit. Is that what you're saying? And the volume in here, which we'll call the cell, the one that went up a little bit, that gets bigger. The volume is forced higher. So again, that's a law of nature, if you want to call it, or a law of how the physics and chemistry work. And it might be useful in some situations, but why could that be a problem if the volume increases over here?
So I just want to make one comment, then I'm going to show you how it applies to the cell.
Okay.
Is that, remember, this is osmosis. So when physiologists talk about this, because the salt cannot pass through, and so the higher concentration literally is sucking the water from the other side. This is actually seen as this makes it osmotically active, osmotic power. When you hear osmotic power, osmotic pull, it means that it's pulling water from somewhere else, okay? The fact that it cannot cross the membrane makes it osmotically active. So let's go to the cell. We talked about sodium, potassium going back and forth. Now we get into the protein. The protein are big molecules, and the protein inside your cell cannot cross the cell membrane. And that's sort of a good thing. Here's your cell making all these important proteins for it to function. If they're going to just leave the cell willy-nilly, you got problems, okay? So proteins are big molecules, and they can't cross the cell membrane. But the fluid right outside the door of the cell membrane has little or no protein, all right? Yeah. So here's the problem. When the sodium and potassium are starting to equilibrate back and forth, right? The chemical concentration, the total chemical concentration inside the cell starts to go up because the protein is not able to cross. And so that what happens in this situation is as sodium comes in and potassium comes out, water comes in with sodium. So you got a problem. So as the sodium comes in and water comes in, then as the water comes into the cell, eventually the cell will die from explosion. So long before the sodium and potassium levels become equal on both sides, the cell will die from explosion. Why? Because the cell membrane, remember, it has a physical nature. It has a limit. It's like a tire. There's only so much you can blow up a tire before it's going to blow on you, right? So the cell membrane then explodes because there's too much water going into the cell.
All right. So I've got this cell with lots of proteins in here. I've got the interstitial fluid around it. It's drawing water in. The cell is slowly expanding, getting bigger and bigger, and you're saying eventually that membrane is going to fail.
Exactly.
Okay. Yep.
And in fact, that's probably how cell death occurs when, we'll get into why that will happen. But so you got a dilemma here. The dilemma is, okay, so we're going to jump through what Jim Tour says. You got a cell and you got a cell membrane, you got everything in the cell. But the very first problem you got right now is you've got intracellular fluid with high potassium, low sodium, high protein, extracellular fluid, interstitial fluid right outside the door of the cell membrane, high sodium, low potassium, low protein, and you've got this is the forces. This is what happens with the laws of nature. This is what we're talking about.
Yeah.
They're working there. Okay. They've got diffusion and osmosis working because that's what happens. We know that's what happens when you get two different solutions separated by in this case, a permeable membrane for the sodium potassium, but semi-permeable for the protein. So this is what's going to happen. So you need a solution. You need to solve this problem.
Yeah, no pun intended with the word solution there.
Yeah.
We got two solutions already. We don't need another solution now. Yeah. So let me restate this, though, because something, this probably you've thought of this for a long time, but it just sort of popped into my mind here as you were talking. We've got these two systems. We've got the interstitial fluid in the cell. A fully permeable membrane doesn't work for the reasons we talked about. A fully permeable membrane won't work, right?
What do you mean it won't work?
Yeah. Well, we can't have a membrane that's permeable to everything.
Of course.
Or diffusion kills us. Okay, so a fully permeable membrane doesn't work. A non-permeable membrane where nothing gets in and out won't work. And a semi-permeable membrane can work for some stuff, but it's going to cause problems for other stuff. So we've got no solution. Sorry to use that word again. We have to use that word, I guess. We've got no solution to this problem simply based on the type of membrane. We have to have something else in addition. We've got to select the right type of membrane. Presumably it's going to be semi-permeable, right? But we also have to have some other engineering prowess that we bring to the table that says, how are we going to deal with the fact that some elements or some molecules come in, others don't, through this semi-permeable membrane? So go ahead. That just kind of jumped out at me.
Okay, so not to put you on the spot, but I've done this a couple of times when I've had a talk. So basically you're in a simple situation, like let's say you're sitting in your boat. Let's say you got this big yacht, okay?
Yeah.
And water is leaking in. Okay, because that's basically what's happening here, okay? The cell, besides the sodium potassium, the key thing that's going to kill the cell is too much water keep coming into the cell. It's going to basically, right? So you got a boat and you've got some leaks somewhere and the water's coming into your boat. What are you going to do? Well, how do you solve that problem?
Yeah, you got to try pumping it out.
Yeah, so you can either bail it out or you can have automatic pumps. I think a lot of yachts have those things, right? I mean, you have to have an automatic pump to get the water out. Okay, so the solution to this problem is something called the sodium potassium pump. So you have something called the sodium potassium pump. It's a molecular machine that's in your cell membrane. You got about 1 million of these. And what it does...
A million where? In your body?
In the cell membrane.
Each cell's got 1 million of these, you're saying?
Yeah, from whatever I looked up, it's several 100,000, maybe up to 1 million.
Okay, so we're talking vast numbers of these things.
Yes. This is how important this is. You have something called the sodium potassium pump. You have these sodium potassium pumps in your cell membrane. They're molecular machines, and they use ATP. So I liken it to, you know how those, it's technically called a sodium potassium ATPase, like an enzyme for ATP. So you know how people have those lights with the solar panels on them and in their gardens and, or along their sidewalks at night. Yeah. So think of this, the ATPase is like a solar panel sitting on this molecular machine, this pump. And it needs energy because what it's going to do, what it does, it's always pumping sodium out of the cell and pumping potassium back in. So what it actually does is it pumps 3 ions of sodium out of the cell, and then it pumps 2 ions of potassium back in. And that requires a lot of energy because it's like moving the sodium against a hard driving wind. I come from Toronto, Canada, grew up there. So, if you're walking in the middle of the winter and you got that cold wind against you, it's hard to walk against it. So you've got this concentration gradient. The sodium is itching to get into the cell. I mean, because it's 140 on the outside and it's only 10 inside. So it's just pushing its way in there, right? And the pump has to send the sodium back against this gradient. And likewise, the opposite. The potassium is 150 inside, only 5 outside. So the cell is just pushing that. The potassium wants to get out there. And so it requires a lot of energy to push the sodium against the concentration gradient. Now, 2 things. Number one is that when you're at rest, sleeping, 1/4 of all the energy your body uses is doing this in all your cells. So several 100,000, maybe million sodium potassium pumps in your 30 plus trillion cells use up 1/4 of all your energy when you're at total rest. But here's the second thing. Because the sodium is pushed out, what happens? The water doesn't come in. Okay. So as the sodium comes in, because the sodium is being pushed out, the water stays out into the extracellular fluid. And this is how the cell maintains its volume and concentration gradient. Its chemical contents.
Right. Okay. So you're saying at rest, I guess it'd be a little bit less during the active day, but at rest, you're saying as much as 1/4 of all of the energy that the body is using is simply used to maintain the cells with their correct volume and their correct chemical constituents so they can keep working. I mean, that's just pure maintenance. That's not running, jumping, flying, diving, all things like that. That's just purely maintaining this disequilibrium that we talked about earlier between the cell and the environment. That's a lot of energy.
Right. Well, and the thing is, and my understanding is that for nerve cells, it may be 40 or 50% of what for nerve cells. And this is talking 1/4 for the whole body. Now, the question, of course, is to have the sodium potassium pump, you got to ask yourself, well, where did it come from? Obviously, if you look it up online, it just basically says it evolved. Okay.
Sure.
What could also say maybe the other line would be that selective pressure let it emerge and then it was conserved. But anyway,
turn this into comedy hour here.
Yeah. The thing is that I looked it up and basically there's 2 parts to this molecular machine. And one part has like 1,100 amino acids. It's made of 1,100 amino, and the second part has 100 amino acids. So you need foresight to know in advance, as Marcus Eberlin has reminded us, that you have to know about diffusion and osmosis ahead of time, that you're going to have to stick this sodium potassium pump. And not only the sodium, but how many you're putting in. Like if you got a yacht, right, and you've got a bailing pump, you got pumps there. Well, maybe you got to have 15 or 20 of them, maybe one or two, depends on the capacity. You got to know what you need. So all of those, that's sort of where what we're talking about, to come to the end here basically is that this is an innovation, because this is when you leave diffusion and osmosis to their own devices, it's going to cause the cell to die.
Yeah, well, that's pretty remarkable, and certainly it does speak to foresight, some real significant engineering prowess to understand what's going to diffuse, how much it's going to diffuse, how much we need to counteract that, how we're going to counteract that with this system. And we haven't even talked about, of course, how you get ATP, which is a whole separate conversation, right, to run this pump. But having this sodium-potassium pump is really remarkable, and thank goodness we have that so that we can maintain our disequilibrium from the environment, Howard, and continue to have this wonderful conversation we've had today.
Yeah. I just added a bit of an anecdote. One of the things one of the lines I like from Steve Laufmann, as my co-author, is that the Darwin's theory is basically a thought experiment, and he compares it to Einstein's thought experiment. But now, over many years, most or probably all of what Einstein predicted in his thought experiment has been found to be true, whereas what we're seeing with Darwin, most of it's probably false now that we actually know how life works. So here's an example, because the idea that the laws of nature can bring on life on its own. And a little anecdote, I encountered a gentleman several years ago who was strict atheist. He said he believed in Darwin's theory, but he admitted he didn't know a lot about biology. And I remember commenting, saying, well, here I'm a physician. I pretty well know a lot about how the body works. And I disagree with you. But I said, let's say if you're talking about a thought experiment, with respect to engineering and physiology or medicine, if your thought experiment is not working, that's like either the machine dies or the body dies. Okay, the Darwinists never have to deal with that. They just say, well, it's there, it evolved, and they never talk about death or how does something stay alive. Yeah. So I asked him, how do you die? And he said, well, when your heart and your breathing stop. I said, okay, but why do you die? And he thought, well, it's probably because you don't have not enough new oxygen going to the brain. I said, well, yeah, that's right, but why does the brain die? And I said, why do you die then? I said, and he didn't really have an answer. So I explained, well, when the brain cells die, especially the cells in the respiratory center that tells you to breathe, once those cells die, then you don't have anything in your brain to tell you to breathe. So it's pretty well game over. But I said, one more question. Why do those brain cells die? He had no answer. Well, here's your answer right here. Okay. We just said that 40 or 50% of the nerve cells in your brain need oxygen. They're using it all the time for your sodium potassium pump. And when you don't have oxygen, the sodium potassium pumps fail and diffusion and osmosis do their thing and the cells explode. That's basically how you die. Yeah. So this is an important point to understand how important this is.
When you equilibrate with the environment, and that's the end of the story. All right. Well, Howard, thank you so much for being here to help us understand some of the deep challenges that have to be overcome in order to produce and maintain living organisms. I'd love to have you back to continue our discussion, if that's all right.
That would be great.
Thank you for listening to this episode of ID the Future. To learn more about the remarkable engineering of life, join us again at idthefuture.com or on your favorite podcast app. And please consider sharing a link with a friend. For ID the Future, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.